A cache is pretty much the secret weapon that makes your processor feel so fast. It's this small, super quick little area for data to hang out in. But all that speed isn't just chaos, oh no. It's all governed by a very strict set of rules or policies that tell the cache exactly what to do. All right, so let's crack open this rulebook and see how it all works. The whole challenge really boils down to this one thing. The cache is just a tiny, temporary copy of the gigantic main memory. And because it's so small, its controller has to constantly make some tough decisions. These choices fall into three big questions. First, what do we do when new data gets written? Second, what gets kicked out when we run out of space? And third, when should we even bother bringing new data in at all? Okay, let's tackle that first problem. When the processor writes some new information, like updating a variable, we've got a potential issue. The super-fast cache has the new value, but the original, much slower main memory is still holding on to the old one. The write policy is the rule that decides how we keep these two in sync. So there are two main ways to handle this. First up is write through. This is the safe, simple, by-the-book approach. Every single time the processor writes to the cache, the controller immediately writes that exact same data all the way back to the main memory. It keeps everything perfectly consistent, but it's also slower because you're always waiting on that sluggish main memory. The alternative, write back. This is the live fast option. The controller only writes to the cache, which makes the whole thing incredibly quick. The main memory only gets updated way later, right when that specific cache line is about to be kicked out. Now you're probably wondering, how does a write-back cache even know which lines have been changed and need to be saved? Well, that's where this really clever little trick comes in, the dirty bit. It's just a simple status flag. When the processor writes to a cache line, the controller flips this bit to true, which marks the line as dirty. It's basically telling the controller, hey, this data is newer than what's in main memory. Don't you dare throw me away without saving me first. It's the absolute key to making the high-speed write-back policy actually work without losing your data. All right, so we've got writes handled. But what happens when the cache is totally packed and the processor asks for a piece of data that isn't there? That's a cache miss. To make room for the new stuff, something old has to go. The item that gets chosen to be kicked out is called the victim, and the replacement policy is the rule for picking it. One really common and very predictable method is called round robin. Honestly, you can just think of it like dealing cards. There's a pointer, or a victim counter, that just points to one line in a set. When an eviction needs to happen, that's the victim. Then the counter just moves to the next line in the sequence, 1, 2, 3, 4, and when it gets to the end, it just wraps right back around to the beginning. It's simple, it's orderly, and it's extremely predictable. The other main way of doing things is pseudo-random. And just like the name says, instead of that predictable, orderly cycle, the controller just randomly picks a victim from the available lines. There's no sequence at all. It's interesting because most ARM cores actually support both of these policies, which gives designers a choice between being predictable or being random. And as we're about to see, that choice can have some massive consequences. And that brings us to our final big question. Just because we have a cache miss, does that mean we should always bring the new data into the cache? The allocation policy is what decides when a cache line actually gets created. You can think of it as the bouncer at the door of the cache club, deciding who gets in. So most ARM cores use something called a read-allocate policy. What that means is a new line is only brought into the cache when the processor tries to read data that isn't there. But if the processor tries to write to an address that's not in the cache, the data just gets sent straight to main memory, bypassing the cache completely. The other strategy is read-write-allocate, which is a bit more aggressive. It'll allocate a line on either a read or a write mess. Now, that might sound more efficient, but there's a hidden cost for writes. The cache has to do all this extra work of fetching the entire line from memory first, just so it can change one tiny part of it. Okay, so we've got our three types of policies, right? Write, replacement, and allocation. Now let's jump out of the textbook and into the real world to see how these rules are actually mixed and matched in real hardware. What's so fascinating when you look at a table like this is that it becomes really clear there's no single best setup. Check out the ARM 720T. Simple, safe, write-through with random replacement. But then you look at the ARM 920T, and it gives designers the choice of the faster write-back policy and lets them pick between random or round-robin replacement. And then you see the Intel X scale, which is the only one on this list that even supports a write misallocation policy. Each one of these combinations is just a different set of trade-offs between cost, performance, and complexity. And these choices, they aren't just academic thought experiments. They have a direct and sometimes really dramatic impact on performance. So let's look at this wild example, where the seemingly harmless choice of a replacement policy leads to a complete and total performance catastrophe. Okay, so here's the setup. We're using an ARM940T, and it has something called a 64-way set associative cache. Now, don't worry about the fancy name. Just think of it as a filing cabinet with a specific section that has exactly 64 drawers, or slots. Our test code is going to read exactly 64 items that all want to go into that one section. It's a perfect fit, right? Every piece of data gets its own little slot. And the results are exactly what you'd think they'd be. The test runs in 0.51 seconds, and it doesn't matter one bit if we use the predictable round-robin policy or the random one, since the cache never actually gets full, no evictions are needed, so both policies perform identically. Everything's fast, everything's efficient, so far so good. But this is where it gets really interesting. We've filled up all 64 slots. What do you think happens to our performance if we try to read just one more item, a 65th piece of data that needs to go into that same, now full section? Whoa, just look at these results. It is staggering. With the random policy, the time barely even moves, just from 0.51 to 0.58 seconds. But with round robin, the execution time just explodes to 2.56 seconds. That's nearly a 500% increase in time, all because of one extra piece of data. So what on earth just happened? What we've just seen is a classic computer science nightmare. It's called cache thrashing. It is this vicious cycle where the system spends all of its time repeatedly loading data into the cache, only to immediately have to kick that same data out because it needs it again right away. It's basically the performance equivalent of sprinting on a treadmill and going nowhere. And this is the brilliant part. The round-robin policy failed precisely because it was predictable. Think about it. When the code asked for that 65th item, the policy predictably kicked out the very first item to make room. But guess what the code needed next? The first item again. So to bring back the first item, it kicked out the second. Then it needed the second, so it kicked out the third. You see the pattern? It created a perfect destructive loop, just thrashing the cache and grinding performance to a halt. The random policy avoided this because it would just pick a different victim each time, and that was enough to break the cycle. Okay, let's wrap this up. First, every cache has a rulebook with 3 main chapters: how to write, what to replace, and when to allocate. Second, going faster often means more complexity, like that clever dirty bit you need for the speedy write-back policy. Third, predictability can be a double-edged sword. As we just saw, the orderly round-robin policy created a disastrous thrashing nightmare. And finally, what this all really shows is that cache design isn't about finding one perfect answer. It's all about balancing these critical engineering trade-offs. And that really leaves us with a final big thought. If something as simple and predictable as round robin can fall into such a catastrophic performance trap, it just raises this huge question for engineers. How do you possibly choose the right set of rules for a device, like the one in your car or your phone, that absolutely must be both consistently fast and utterly reliable? That right there is the constant challenge of system design.